This first problem we want to go over is a relatively easy one, but it does illustrate an approach without going into too much detail. You're going to see the spectra of a molecule with a formula of C5H8. Here's the infrared spectrum. You can see the various peaks and settlings there. The 3000 region's interesting, but we'll get to those fine points in a minute. Here is the carbon NMR spectrum. You'll see that there are 5 peaks right here, 4 in this region, 1 in another, fairly standard stuff. And then this is a rather complex NMR spectrum, but remember, our task is not to account for every peak in the NMR spectrum, it's to solve for the structure. So how do we get started? Well, if you refer to the last presentation, we make some initial observations. The formula C5H8 allows us to denote that the degrees of unsaturation is equal to 2. There are either 2 pi bonds or a pi bond and a ring or 2 rings. If you'll recall back to the carbon NMR spectrum, you'll note that it had 5 peaks in a formula of C5, which means that there's no symmetry. The infrared spectrum showed us peaks at the 3000 region, both to the left and right of 3000, meaning that there are protons on both sp2 and sp3 carbons. And the last thing to do finally there is the proton NMR, where the integrals, we can look back here, show us integrals of 1, 4, and 3. All 8 protons are in that region. So let's look at the IR again. We can see that there's a peak here in a low 3000 region and just shy of 3000 for CHs, both on sp2 and on sp3 carbons, as you learned last semester. There's a big peak here, but with no heteroatoms, it's not clear what this is. Perhaps we'll talk about that near the end of the problem, but it's nothing that's going to help us in our analysis. So if we our unsaturation degrees were 2, the question we might ask is, do I have pi bonds or do I have rings? And that's an easy question to answer. If you look at the carbon NMR spectrum, you'll see that there are 4 peaks above 100. That tells us that there are 2 C double bond Cs in our molecule, and as a result we have there are no rings. There's one other carbon in a region near 20 parts per million. That's a regular sp3 hybridized carbon, and thus you now have 3 pieces for your molecule. A C double bond C, another C double bond C, and a carbon. Just to look at the spectrum again, here are the 4 peaks that tell us we have 2 C double bond Cs, and here's our 5th carbon, which is in the standard sp3 region. Now, the next question we might ask is, are there protons on the C double bond C? Of course there are. We learned that from the IR already, but if we look in the left-hand side of the spectrum, that is to say the region past 4.5, we can see that the integral tells us that there are 5 protons directly on alkene carbons. What that means is if you have 2 double bonds and you have 5 protons on there, there's only 2 ways they can assemble together. Either 3 on one, 2 on the other, 3 on one and 2 on the other, but on different hydrogens. There's no other way you can put it together. If you had 2 CH2s bonded together, that would be a complete molecule and there'd be no way to tie the atoms together. And so here are our 5 protons that are attached to the double bonds in some way, shape, or form. And here's everything else. And everything else has an integral of 3. That means it's a methyl group. Its chemical shift is near 2, which means it's attached to an sp2 carbon. It would be at about 1 if it were attached to a regular alkane. The most important thing about it, though, is that it is a singlet. And since it's a singlet, that means it must be attached to a carbon that has no protons on it. And so if we go back to our pieces and now say there's got to be a methyl group attached to this double bond, there's no place where we can attach a methyl group that wouldn't have splitting. Here, though, there is a carbon that has no protons on it, and so now our two pieces look like this. And once you have these two pieces, there's only one way they can come together and make a molecule, and that is to form a diene in this way, and that is indeed the structure. It is isoprene. And so that is the structure of the problem solved, but you should never finish there. You should always go back and make sure that the spectra are consistent. We have CHs, both double bonding and single bonding carbons. This big old peak is tough to describe. It's actually due to some rocking motions of these terminal CH2s, but they're not really part of what helped us solve for our structure. Once again, there are 5 peaks in the carbon NMR spectrum, no symmetry. 4 of them are double bonds. 1 of them is not. And finally, we have a singlet for the methyl group that's not coupled to anything around 2, and our other 5 protons are here. This is maybe a somewhat curious situation in terms of the multiplicity. Luckily, we didn't need it in order to solve the structure, but the reason why it's so complex is that the hydrogens on the same carbon are not identical. This hydrogen that's cis to the methyl group will have a slightly different shift than this hydrogen that is cis to the alkene group, and they'll actually couple to one another because they have different shifts. Likewise, that's going to happen here, and then there'll be further coupling here, and so all in all, we have a very complex array of peaks, but none that are going to interfere with our solving the structure. We don't have to assign all of these peaks. We just need to know that there's 5 protons in that region. So while this is a rather simple example, it incorporates many of the things we want to think about when we're solving for a more complex structure. This is going to be progressing towards more complex problems, and then you'll be able to confidently do your own structure work.